What is a chemical reaction? It is a process in which substances are combined or broken down to form a new substance. There are two types of change, physical and chemical change. A physical change is when a substance undergoes a physical change without any new substances being formed or destroyed. An example would be a rock breaking. It obviously is changed physically, but no new substances have been formed. A type of physical change a lot of people mistake for chemical change is a change of state, such as water freezing or dissolving something in water like salt. Because even if the physical characteristics like the toughness or texture change, it is still chemically the same. A chemical change is when two or more substances combine or break down to form a new substance. You can distinguish it from a physical change because the chemical reaction usually results in a permanent color change, like when you burn toast, a gas being given off, like when you open up a can of soft drink, a solid or precipitate being formed, like when you combine sodium chloride and silver nitrate, or energy is being absorbed or produced, like when you light a match and release light and heat, or when you use a cold pack and it absorbs the heat energy around you so it becomes cold. There are 5 major classes of chemical reaction. Synthesis, when 2 or more simple compounds form to make a more complicated one. Decomposition reactions, when a complex substance breaks down into a few simple substances. Single displacement reaction, when one element trades places with another element in a compound forming a new substance. Put simply, it is when there are 2 compounds and one element from one compound moves into the other compound. In a double displacement reaction, the positive and negative portions of 2 ionic compounds interchange. In a combustion reaction is when a substance rapidly combines with oxygen to form one or more oxides and releases energy. Acid mine drainage impacts stream and river ecosystems through acidity, ferric ion precipitation, oxygen depletion, and the release of heavy metals associated with coal and metal mining, such as aluminum, zinc, and manganese. When mineral deposits that contain sulfides are mined, they have the potential to produce acid mine drainage. This includes the mining of coal, copper, gold, silver, zinc, lead, and uranium. The mineral pyrite, more commonly known as fool's gold, is iron disulfide. Pyrite is one of the most important sulfides found in the waste rock of mines. When exposed to water and oxygen, it can react to form sulfuric acid. The following oxidation and reduction reactions express the breakdown of pyrite that leads to acid mine drainage. Ferrous disulfide plus oxygen plus water makes iron sulfide and hydrogen sulfide. Iron plus oxygen plus hydrogen makes iron and water. Iron and water makes ferrous oxide and hydrogen. Iron disulfide plus oxygen plus water makes hydrogen, sulfuric oxide, and ferrous oxide. The production of acid mine drainage can occur long after mines have been abandoned if piles of waste rock are in contact with air and water. The red color often seen in streams receiving acid mine drainage is actually a stain on the rocks called yellow boy or ferrous hydroxide, formed during reaction 3 above. Equation 4 shows that by introducing hydrogen ions, acid mine drainage affects the acidity of a stream. Acidity is commonly measured by pH values, which are easy to collect and compare. pH, however, is not always a good indicator of acid mine drainage because it only indicates the concentration of hydrogen atoms. When evaluating the extent of acid mine drainage, it is important to know the amount of hydrogen atoms remaining in solution after the natural buffering of the stream is completed. For example, pH measurements may not detect heavy acid mine drainage in a stream because of high alkalinity due to dissolved carbonates. Assessing the excess of hydrogen ions over basic ions' total acidity is a better measurement of acid mine drainage. Acid mine drainage depletes the buffering ability of water by neutralizing carbonate and bicarbonate ions to form carbonic acid. Once exposed to acid mine drainage, the affected carbonate buffering system is not able to control changes in pH as well. The buffering system is completely destroyed below a pH of 4.2, where all carbonate and bicarbonate ions are converted to carbonic acid. The carbonic acid readily breaks down into the water, and carbon dioxide, which is carbonic acid, breaks down into water and carbon dioxide. Here is a table comparing waters receiving acid mine drainage, acid rain, and peat drainage. The bright orange-colored water and stained rocks are usually telltale signs of acid mine drainage. The orange color is caused by ferrous oxide precipitating out of the water. The precipitate forms as the acid drainage becomes neutralized. At low pH values, the metal ions remain soluble. When the pH rises, the ion oxidizes and precipitates out. Depending on the conditions, the orange-colored precipitates may form inside the mine or several miles downstream. The precipitates can be harmful to aquatic life. The clumps reduce the amount of light that can penetrate the water, affecting photosynthesis and visibility of animal life. Furthermore, when the precipitate settles, it blankets the stream bed, smothering the bottom dwellers and their food resources. Treatment of mine effluent. Today's activity deep mines in the upper reaches of Wheeling Creek follow state and federal regulations for discharging effluent from a mine. Acid mine drainage must be treated to increase pH and remove heavy metals before being discharged into a receiving stream. Treatment commonly consists of adding strong bases such as caustic soda, soda ash, or lime, or calcium hydroxide. Note the color change in the treatment pond picture to the right. The water is red where mine effluent enters the pond. The red color indicates that iron hydroxide is precipitating out of the water column. Mechanical aeration speeds the process by making oxygen more available in reaction 1 and 2 above. The iron precipitate eventually settles to the bottom of the pond, indicating by the area where the red water turns green. The green color is a result from the presence of sulfate, sodium, and calcium ions remaining from acid neutralization reactions. The bases used in the treatment of acid mine drainage work by neutralizing the acidity of the mine effluent. Because they are strong bases, they ionize and dissolve in water. The resulting hydroxide and carbonate ions combine with hydrogen ions, taking them out of the solution. The resulting products are water and carbonic acid. The carbonic acid is relatively harmless because it is a weak acid and can be dissociated as water and carbon dioxide, as described in the bicarbonate buffering system. Water hardness and conductivity are a useful indicator of upstream mining activity. Water hardness may be high in watersheds with active or abandoned mines. Ferrous iron from acid-generating reactions and calcium from acid-neutralizing reactions may contribute to higher than average levels of water hardness. Leftover ions from acid-generating and acid-neutralizing reactions can effectively increase the salt concentration or salinity of the water. The greater the salt concentration, the greater the conductivity of the water, which makes conductivity a very useful indicator of upstream mining activity. The coal-fired Gavin Power Plant in Cheshire, Ohio. The principal cause of acid rain is sulfur and nitrogen compounds from human sources, such as electricity generation, factories, and motor vehicles. Coal power plants are one of the most polluting kind of power plants known to man. The gases can be carried hundreds of kilometers into the atmosphere before they are converted into acid and deposited. Chemical processes. The combustion of fuels creates sulfur dioxide and nitric oxides, they are converted into sulfuric acid and nitric acid. Gas phase chemistry. In the gas phase, sulfur dioxide is oxidized by reaction with the hydroxyl radical via an intermolecular reaction, which is followed by. In the presence of water, sulfur trioxide is converted rapidly to sulfuric acid. Nitrogen dioxide reacts with oxygen hydroxide to form nitric acid. Chemistry in cloud droplets. When clouds are present, the loss rate of sulfur dioxide is faster and can be explained by gas phase chemistry alone. This is due to the reactions in the liquid water droplets. Hydrolysis. Sulfur dioxide dissolves in water, and then, like carbon dioxide, hydrolysis in a series of equilibrium reactions. Oxidization. There is a large number of aqueous reactions that oxidize sulfur from sulfur with a valence number of 4 to a valence number of 5, leading to the formation of sulfuric acid. The most important oxidization reactions are with the ozone layer. Hydrogen peroxide and oxygen. Reactions with oxygen are catalyzed by iron and manganese in the cloud droplets. Acid deposition. There are two ways of acid deposition. Wet deposition. Wet deposition of acid occurs when any form of precipitation, such as rain, snow, and so on, removes acids from the atmosphere and delivers it to Earth's surface. This can result from the depositing of acids produced in the raindrops, see the aqueous phase chemistry above, or by the precipitation removing the acids either in the clouds or below clouds. Wet removal of both gases and aerosols are both of importance for wet deposition. Dry deposition. Acid deposition also occurs via dry deposition in the absence of precipitation. This can be responsible for as much as 20 to 60% of total acid deposition. This occurs when particles and gases stick to the ground, plants, or other surfaces. Prevention methods. Many coal-burning power plants use flue gas desulfurization, FGD, to remove sulfur-containing gases from their stack gases. For a typical coal-fired power station, FGD will remove up to 95% or more of the SO2 in the flue gases. An example of FGD is the wet scrubber, which is commonly used. A wet scrubber is basically a reaction tower equipped with a fan that extracts hot smoke gas from a power plant into the tower. Lime or limestone in slurry form is also injected into the tower to mix with the stack gases and combine with the sulfur dioxide present. The calcium carbonate of the limestone produces pH-neutral calcium sulfate that is physically removed from the scrubber. That is, the scrubber turns sulfur pollution into industrial sulfates.